Hello everyone and welcome to this continuing series of lectures on digital system design. In this set of lectures we are going to look at sequential logic modeling, in particular using Verilog, and also talk about some aspects of synthesis and what exactly does it mean to talk about synthesizable code to take Verilog and synthesize it into a set of gates. So let's start with the subject of sequential logic modeling. What exactly do we mean here? We have already looked at combinational logic and how we can use the assign statements as well as always blocks in Verilog in order to implement the basics of how to model the behavior of combinational logic. Now we would like to move to sequential, right? And first let's sort of contrast the two. What exactly do we mean by combinational or sequential logic? First things first, combinational logic is logic where the output depends only on the current inputs. Examples of course are the usual gates, the AND, OR, NOT, XOR, the various kinds of logic gates that we start out learning in the Introduction to Digital Systems course. What about sequential logic? The output depends on the current inputs and also crucially on the history. What do I mean by history here? What it means is previous computations, previous values of any of the signals that are involved in the computation, right? Any logical operation, any logic gate can be thought of as performing a computation. Now you may not really think of it as a computation because it's just an AND gate or OR gate, it's something fairly simple, but well, so is addition, right? So in that sense any logical operation is thought of as a computation, and the inputs and outputs of computations are the values that we are interested in. Now if there is some way by which I can talk about previous values or the past values of a given signal, then we have a concept of history, or more accurately memory, associated with the signal. In particular, what we will see as we move forward is you don't in general remember every single past value. You sort of take snapshots of the history of a signal and say at these time instants the signal had specific values. And by storing those and saying I'll perform a computation which is dependent on those past historical values as well as my present inputs, it vastly increases the complexity of the computations that we can perform. Now a crucial aspect of this is the notion of a so-called clock signal, right? And a clock can be thought of as, we often refer to it as the heartbeat of a digital synchronous circuit. It essentially ensures synchronization of operations, right? It means that there is a specific beat, a regular interval at which certain operations are allowed to take place. In particular, it controls the precise time when values are allowed to change. Okay, what exactly that means? Hopefully you are already familiar with the basic operation of a D-type flip-flop, but in terms of the implications it has on how we write code and how we design systems, that should become clear as we move forward. Now in hardware description languages, the basic clock is a very simple idea, right? There is somehow I need to generate a signal that toggles, meaning that it goes from 0 to 1 and then back to 0 and then back to 1 and then back to 0. It keeps toggling back and forth between 0 and 1, and it does so at a regular interval, right? How long is it 0, how long is it 1? That in turn determines something called the duty cycle. But actually speaking, in many digital synchronous circuits, we don't really care too much about the duty cycle. In particular, we are not particularly bothered about whether it is 50%, that is half the time on, half the time off, and so on. And the reason for that is that we are specifically interested in the edges of the clock, when the clock transitions from 0 to 1, or in some cases from 1 to 0, right? So this notion of a clock that transitions at regular time intervals is a very simple and straightforward idea. In terms of an electrical signal, this is basically what we would call a square wave, right? Something that just has some kind of a shape like this, going up and down at regular intervals. And of course the implicit understanding is that the clock has a fixed time period. We rarely have clocks that sort of look like this, although in principle there's nothing wrong with having a clock that looks like this, right? But in practice we would always typically tend to have a constant time period and therefore equal amount of time up and down and so on. But that's the most basic version of the clock. Complex digital circuits typically involve multiple clocks and those are usually sort of segregated into what are called clock domains. Within each domain we are synchronous, meaning that all the flip-flops operate with the same clock. But the moment you try transferring data between domains, this business of synchronization is a fairly complex problem that you need to pay close attention to. We will talk a little bit about it later, but for the time being we are just going to, I just want to mention it and move on. And in practice, when you're building large circuits, it turns out that clock distribution is actually a very complex problem, right? Part of the reason for this is because reality kicks in, and getting an electrical signal to be able to switch at a high frequency and also to propagate across an entire chip without any sort of significant delay associated with it is a hard problem, right? It also tends to consume a lot of power. So there are a number of issues why clock distribution actually ends up being a fairly complex problem on its own. For the time being we are going to ignore all of that. This course is primarily going to focus on digital system design. It is more at a higher level than the introduction to digital systems, but at the same time there are many aspects that come in when you would actually go down to a full application specific IC that we will not be considering, and things like clock distribution are one of them. So clock edges, right, I already mentioned the notion of an edge in a clock, and this is typically how clocks are represented, right? The waveform, the timing diagram representation would look something like this. We would talk about a signal that's going 0 to 1 high and then again goes low, remains low for a while, once again goes high, and so on. And what you can see over here is I have put arrows on all of these edges that are going from 0 to 1, right? And effectively those edges are what are called the positive edges, or in Verilog terminology the pos edge, right? Similarly, the falling edges over here are what are called the negative edges or the neg edge, right? So the negative edge is basically going from 1 to 0, the positive edge is going from 0 to 1. This is just convention, it's terminology. I mean, of course it makes sense to call positive when you're going from 0 to 1 and negative when you're going from 1 to 0. But why are we particularly interested in one or the other edge? That turns out to be a matter of convention. And as you will see, in most circuits or in most designs we tend to use the positive edge. Now why is that? Is it because it turns out that the actual 0 to 1 transition is somehow better than the 1 to 0 transition? Not really. There could be some specific kinds of circuit topologies where a positive edge is more, has a better rise time or has some other kinds of properties that make it better suited than a negative edge. But in general that's not the reason, it's just that we had to choose one. It's like driving on the left side of the road versus the right side of the road. You pick one and more or less try to stick with it as far as possible. So most likely in most of the code that you see, you are likely to see pos edge of clock. That does not mean neg edge cannot be used, but in general it's not a good idea to mix the two, right? Unless you know exactly why you are doing it. There will be scenarios where we will actually be looking at something of that sort. Incidentally, this diagram is actually slightly wrong, right? I need to correct this. It should actually look like this. The negative edge is the one that's here. So what should happen is that this transition should be at this point. This is the actual negative edge, right? So what we have over here is you have the pos edge signal. Essentially what we are saying is that there is a signal that transitions at this point and that corresponds to the positive edge. Now you might notice in this diagram the way that I have written or drawn it, right? There is a slight delay. In other words, the pos edge seems to be at this point corresponding to this dotted line, but the actual signal changes a little bit after that. And this is to at least remind us that physical reality exists and that no signal can sort of instantaneously change at this point in time. If I have an edge over here and there is a change in a signal that comes about because of that edge, there will be a small delay, there will be some amount of delay, and there will be probably a rise time associated with the corresponding signal going from 0 to 1, or it could be from 1 to 0, okay. So the way that this diagram is drawn over here, actually both of these signals are positive edge, they are changing on the positive edge. This other one that I have drawn in blue over here actually corresponds to a transition on the negative edge, which is basically the falling edge of the clock signal. Now as I said, it's not just for these signals. In reality, even the clock itself is a real physical voltage somewhere on the circuit, which means that this sharp rise that we have shown over here is unrealistic. That's not what happens in practice. There is always going to be some amount of a slope over here, some rise time, correspondingly a fall time over here, right. There could also be overshoot, right, where the signal goes slightly above and sort of settles down to its final value, undershoot where it goes below 0, right, actually going below the ground voltage for temporarily, the slope with which it transitions out here, right. And during this transition, it is also possible that you actually have both types of transistors that are involved. We have not spoken about transistors or how gates are implemented so far, but in reality gates are implemented using transistors, and during this slope time it is quite possible that two different sets of transistors turn on and you actually end up having a short circuit or a small amount of current that just flows between the supply and ground, almost like a short circuit, right. Those are all real physical characteristics that, especially when you are doing high speed digital design, where high speed typically corresponds nowadays to even more than hundreds of megahertz. Typically only when you get into the gigahertz or close to that range you need to worry too much about these issues, but they are considerations to keep in mind. For now, we are going to ignore all of this and assume that our clock is a very neat little signal that just has a perfect square wave shape. Alright, so how would we write code in Verilog to implement something like a flip-flop, right? And this is what I would call the traditional style of coding. Essentially what it says is this: there is an always block. You already know what an always block is. It basically is some kind of a behavioral way of describing the behavior of the circuit, right, or a procedural way of describing the behavior of the circuit. Why do I call it procedural? Because what we are saying is that there is an always begin end block, and whatever is there inside the begin end, I mean, it's optional to have the begin end, but typically we do have it. And if there are multiple statements in here within the begin and end statement, those happen one by one in sequence. So that sort of runs like a procedure in a programming language. So that's what we mostly mean when we talk about procedural description. This is how we would write it. And if we look at this code and try to understand what it's saying, it basically says look for the positive edge of a clock, and if you find a positive edge of the clock, then take two other signals unrelated to the clock, possibly unrelated to the clock, right. D is the input because it comes on the right hand side of the equation, Q is the output because it comes on the left hand side of the equation, and say that Q will get the value from D. Okay. So what does that mean? That more or less seems to indicate something like this: wait for the positive edge of the clock and take this 0 and convert it into a 1, assuming that 1 was present at the input of whatever circuit I am trying to build, and this 1 needs to come through to the output. So what is the circuit that has this kind of behavior? If we think about it, this looks precisely like the behavior of a D-type flip-flop, right? I have a clock over here, I have a D input over here, and I have a Q output. And if I have this kind of a structure, my understanding is that this performs precisely the functionality described out here, right? It waits for the positive edge of this clock, takes the value of D and copies it over into Q. Okay, so very simple, right? It allows us a nice neat way of implementing one particular kind of sequential logic element. The core difference between this and a piece of combinational logic is the fact that the sensitivity list over here, you will notice that first of all it has the pos edge of the clock and not just the clock, right? The second is it does not have D as part of the sensitivity list. What we are saying is the output Q over here does not actually depend on changes in D. I don't care when D changes, I only care when clock changes, and only then I need to be able to take whatever value is there in D and copy it over into Q, right? This is fundamentally different from how a combinational logic works. In combinational logic, everything that is on the right hand side over here would be in this sensitivity list, and I would say okay, anything changing over here, promptly go and update it. Now the other thing you might notice is that when we talked about combinational logic, the assignment statements would typically just have been a equal sign, whereas over here we have the less than equal sign, which is the so-called non-blocking assignment, right? This is important. You cannot afford to ignore this, or in general this is the right way of modeling sequential logic. Also, it should be used only when you are modeling sequential logic and not for combinational logic. Okay, the modern style, which is a preferred way but works only with SystemVerilog, right? It does not work with traditional older versions of Verilog, but pretty much most tools that you are likely to use today support SystemVerilog, right? What this does is it says don't just use always, use something called always underscore ff, okay. Now what does this mean? It basically says that it's sort of making explicit the fact that we want this always block to infer a flip-flop, right. Similarly, there is also an equivalent always underscore comb or comb, which basically translates into always combinational logic, right. Now why do we have these two things? It's because this getting the sensitivity list right turned out to be a common source of errors in a lot of Verilog coding. So it was sort of decided finally by the people maintaining the Verilog standards, or when they moved to SystemVerilog, that it makes sense to actually just make it explicit and say yes, we want a flip-flop over here, no questions asked. Now of course you still need to provide the passage of the clock because it doesn't know which clock you are going to use. Just because the signal was named clock over here does not mean it's going to infer it as a clock. You need to tell it which signal to use as a clock and then tell it what to update at the output. So as I said, always ff is the modern actually SystemVerilog syntax, not exactly Verilog, but I'm for all practical purposes here treating SystemVerilog as sort of a superset of older versions of Verilog. Now this clock edge has to be in the sensitivity list and this non-blocking assignment is required. Well, even if you just put a regular equal sign over here, it will work, but it is going to be a source of errors at some point in time. So as a matter of habit, you should make it such that every time you want a flip-flop behavior, you use a passage clock, and in here you essentially use non-blocking assignments. So let's take a look at this structure of what we have over here, and this is just essentially what a D flip-flop looks like. Let's quickly just put in the signals out here, right, for reference. And what we have is, what I've shown over here is essentially the timing diagram corresponding to the behavior of a D-type flip-flop, right. And as you can see, I've defined the module basic DFF. It has an input wire clock, another input wire D, and an output reg Q. Now once again, with SystemVerilog I wouldn't be using wires and reg over here, I would just be declaring them as logic, right. But as I said, I'll be sort of using these interchangeably, sort of switching back and forth between the two. It's probably a good idea to get used to both of those, but in general, for the most part, we'll try and stick to logic to avoid any possible confusion with wire and reg, except when we are trying to sort of make a point, right, that you can get confused. So be prepared for it. Make sure that you understand both of these, because it is very likely that you will encounter some Verilog code at some point in time that still uses the older conventions and therefore works with wire and reg rather than with logic. So as I said, this style of coding would result in a D-type flip-flop. The schematic symbol is this, and let's just look at the behavior out here, right. Ignore the numbers that are up here. We are essentially interested in the signal itself. And as you can see, this first positive edge is probably out here, but it's sort of out of scope of what I have. So I'm going to start with this edge over here at the time instant marked 4, okay. There's another positive edge at 8 and another positive edge here at 12. Now let's look at the D input. As you can see, it sort of remains at 0 for a while, and then I'm saying that it has changed somewhere, and as you can see, it changed at some point that has nothing to do with this positive edge. Now you might wonder, how could that happen? And well, the answer is simple. This happens all the time, and it could happen for two reasons. One is that D might actually be coming in from somewhere outside the circuit, so it doesn't really know of the existence of a clock, and what you are trying to do is synchronize it, get it in line with the rest of the clock. That's one part of it. But an even more sort of common scenario is that D is actually the output of some multiple computations that are happening somewhere else, right, based on the values of other flip-flops and inputs and so on. And as a result, it actually takes some time for D to change to its value that it has over here. So the bottom line is, there is absolutely no requirement that D must change exactly corresponding to a positive edge of the clock, right. And the whole point of the clock is that it makes sure that it doesn't matter where D changed, it takes care that Q can change only at the positive edges of the clock. And as you can see over here, Q, the first change in Q happens immediately after the first positive edge of the clock. Now how do we decide whether it changes or not? Well, at this time instant, we go look at the value of D. It turns out that D has a high value. Q was originally low, so I am going to sort of make it transition from low to high. Then I just move forward until the next positive edge. At this positive edge, once again I sample the value of D, right. So this term sampling is again something that we will commonly come across. It is not really the same as sampling in the sense of what you might come across in signals and systems or a signal processing course. It is related at some level, but we don't talk about things like the Nyquist criterion or sampling frequency and so on. Over here, sampling just means I have a clock edge. At that point in time, I go look at what the signal is. Okay. And over here, it turns out that even though D underwent some transitions out here, at the moment of the pos edge, D had a value 0. So what should I do? I need to make the value of Q low. Now, it turns out that immediately after that, D became high. But the point is that is after this clock edge. At this time instant, I actually end up seeing 0, and therefore that is what comes through here. Now, some of you hopefully are already thinking this through and saying, hey, these are real wires with real delays, capacitance and so on. At least that's what I've been talking about so far. Isn't there a chance that this clock edge comes slightly delayed? So how do I know that I'm not going to see it over here, or even worse, that I'm going to see it somewhere during this transition period? What happens if something like that happens, right? And yes, it's entirely a possibility, right? And in order to make sure such things don't happen is why we need to have constraints on timing, okay, which we will get to later. Right now, all that we care about is the third positive edge comes, I once again go sample the value of D, and it turns out this time it's high. So my Q once again has to go high. So you can see that D basically underwent multiple up-down transitions out here, but Q underwent transitions exactly at the positive edges of the clock. If it turned out that here, for example, this had just been high, then this transition would not have taken place at all. This entire distance, it would just have been flat. Okay. Alright, so now let's take this further. So far we have talked about a single flip-flop. I could easily also write code that essentially says I have this input wire clock, no other input, I don't have a D input for example, but I have an output reg which I am defining as a 2-bit value, a counter, right? And what I do with this counter is that I say basically on every positive edge of the clock, I am basically going to go count is equal to count plus 1, okay. Now, what exactly does this mean? The first thing is, you look at this, and if you think in terms of an equivalency function, you might wonder, okay, count looks like it's a variable declared somewhere. Of course, in this case it's an output. You don't really have a concept of an output variable in C, but maybe you could think of it as a return value. I would still need to declare it as a variable somewhere. So what would I do with it? I would basically say that I have this count and I need to do something with it. And what I'm going to do in this case is to basically say that I want to increment its value by 1 every time there is an edge on the clock. So what does this mean? As you can see over here, count has been declared as a 2-bit register, right? Remember the Verilog syntax. If I declare something as reg of 1:0, this 1 corresponds to the most significant bit, this 0 corresponds to the least significant bit, and this essentially corresponds to an array of bits or a group of bits, right? A multi-bit value. So count in this case is a 2-bit value. On every clock edge, I'm going to do count is equal to count plus 1. Now, for the sake of simplicity, let me assume that count starts from a value 0, or in binary 0, 0, okay. So this is what I have here. Essentially, count starts off with a value 0, and what I say over here is every time there is a pos edge of the clock, take the present value of count, add 1 to it, and put that value into count again, right. In terms of the waveform, this is what it looks like. After this pos edge of the clock, count has taken the value 1, which is basically binary 0 1, right. So this is 0 0, this is 0 1. After that I again go to count is equal to count plus 1, it becomes 1 0, which is 2, and then it becomes 1 1, which is 3. After that I increment further, but remember that count is only a 2-bit value, so effectively it overflows, it tries to become 4, it cannot, right, and it once again overflows into 0 0, right. The overflow bit is basically discarded because I have only 2 bits of storage, I can't really do anything with the 3rd bit and I discard it, the hardware doesn't really care, okay. Now this is interesting because what it tells you is that it looks as though there is some logic over here, it should be possible for us to get this right, and if I think it through, it will probably require me to have 2 registers out here, both of which are connected to the same clock. The output of these essentially corresponds to the 2 bits of the output. So this would be C1 and this would be C0, right. So this C1, C0 is essentially what I am seeing down here as the different values that come out of the bit sequence, right. And now comes the question, okay, if I have C1, C0 to start with and I want the output to be C1, C0 plus 1, maybe I can create some kind of a logic circuit out here, right, perhaps using half adders, perhaps using full adders, or perhaps using some other, just write out the Boolean equations and simplify them and get 2 outputs, okay. I'll call them C1 prime and C0 prime, and what I'm going to do is to basically take this value of C1 prime, put it back over here, and this value of C0 prime and put it back over here. So this is how you would actually implement it if you were asked to do this in terms of a hardware design, right. It turns out that as far as Verilog is concerned, you can just write a very simple piece of code like this. It will actually infer all the hardware you need in order to implement something of this sort.